configuration, or we can say that stable electronic configuration. So the stable electronic configuration gives the stability to an atom, right? So if the atom is stable, ionization energy automatically increase. How? Either it should be fully filled subshell. In case of beryllium, we have 1s2 and 2s2. Now 2s is a subshell. It's not a shell, it's a subshell. We have discussed this thing in atomic structure. 2s is a subshell, but it is fully filled. That's why its ionization energy will be high. Now, if we talk about nitrogen, it is 1s2, 2s2, 2p3. Now 2p3 means it is half filled, and half filled subshells are stable due to the exchange energy and the symmetry that we have already discussed in chapter number 2. And the last is fully filled shell, and all the noble gases have fully filled shell. We are taking the example of neon. It is 1s2, 2s2 and 2p6. That's why it will be very difficult to eject the electron from the valence shell of neon. So friends, in this lecture we have discussed about the atomic radius, ionization energy, factors affecting the ionization energy. Now we are going to discuss about the variation of the ionization energy in the group and the period. Now let's start with the variation in the group. So as we go down the group, ionization energy decreases. Why? First of all, the number of shells increases. If the number of shells are increasing, then electron will go far away from the nucleus. In first shell, it is close to the nucleus. Second shell, it will be far. Third shell, again far away from the nucleus. So as the number of shells increases, electron moves far away from the nucleus. That's why it is easy to eject out the electron from the valence shell. That's why ionization energy decreases. So a gradual increase in the atomic size due to the progressive addition of the new energy shells. So if the new energy shells increases, ionization energy automatically decreases. Now, second point is, when we go down the group, the shielding effect increases. The intervening electrons, the electrons which shield the outermost electron from the nucleus. So what happens when we go down the group? The effectiveness of the attraction of the nucleus for the valence electron decreases. So increase in the shielding effect on the outermost electron due to increase in the number of inner electrons. Now, you might be thinking, when we go down the group, nuclear charge increases, right? Atomic number always increases. When we go down the group, nuclear charge increases. If nuclear charge is increasing, then number of protons are increasing. Then there will be more positive charge. And if there is more positive charge, it will attract the electron and it will increase the ionization energy. But what happens? There is not only a single factor for ionization energy. There are 5 factors. So the increased nuclear charge is cancelled by the atomic size and shielding effect. What they do? The increase in the atomic size and shielding effect suppress the effect of the nuclear charge. So let us see what happens. Down the group, taking the same example of lithium, sodium and potassium, you can see that in the case of lithium, there are only 2 intervening electrons which are trying to shield the outermost electron. In case of sodium, there are 10 electrons. In the case of potassium, there are 18 electrons. And one more thing, number of shells are increasing. The valence electron is going far away from the nucleus. That's why ionization energy decreases. Let's see the variation of the ionization energy in period. Now, if we move across the period, the number of protons in the nucleus increases and the number of electrons in the same shell also increases. So therefore, size decreases. So if we talk about lithium, there is +3 unit charge. If we talk about beryllium, there is +4, boron, carbon, nitrogen. So what is happening? Nuclear charge is increasing. But nuclear charge is not only the single factor to govern the ionization energy. There are some more factors. Now here, the factors which will dominate, that will be electronic configuration. Let's see how. The nuclear charge is not only factor. There are some more factors. Let us find out what happens in the case of the period number 2. So this is a graph of ionization energy versus the atomic number, and you can see that the ionization energy of lithium is very low. Beryllium, it increases. Boron, it decreases. It should increase because we are going across the period. But in the case of boron, it is decreasing. Then carbon, it is increasing. Nitrogen, again increasing. It should increase for oxygen, it is decreasing. Then for fluorine, it is increasing, and for neon, it is highest. Now our point of concern is why the ionization energy of boron is very less and why the ionization energy of beryllium is greater than boron. And same thing is for oxygen and nitrogen also. Why the ionization energy of nitrogen is greater than oxygen? Let us see the explanation of that. And the explanation is, in the case of beryllium, we have fully filled S subshell. But in the case of boron, we have incomplete P subshell. That's why the ionization energy of beryllium is greater than that of boron. Now in the case of nitrogen, we have half filled subshell 2p3. But in the case of oxygen, we have incomplete P subshell, that is 2p4. That's why ionization energy of nitrogen is greater than that of oxygen, and ionization energy of beryllium, that is greater than that of boron. So that we have to keep in mind, right? Let's move on to successive ionization energy. Now if there is an element that is A in the gaseous state, suppose x1 energy is used to eject out the electron from the valence shell, and we again eject the electron from the valence shell of A plus, then x2 kilojoule is required, and from A2 plus to A3 plus, it is x3 kilojoule is required. So what will happen? In this case, x3 is greater than x2 and x2 is greater than x1. Why? Because the effective nuclear charge will increase in that case, right? So let's move on to some exceptions. Now ionization energy of beryllium is more than boron, we have already discussed. Nitrogen is more than oxygen, that we have already discussed. Gallium is more than that of aluminium. Now in 13th group, there is boron, aluminium and gallium. Gallium is below aluminium, so that's why the ionization energy of gallium should be lower than that of aluminium, but it is more than that of aluminium. Why? Poor shielding effect of D subshell or electrons of D subshell. In the same way, in the 14th group, carbon, silicon, germanium, tin and lead. If we talk about tin and lead, lead should have the less ionization energy, but it has more ionization energy because of poor shielding of electron of F subshell, right? Let's solve one question. Now this question is based on ionization energy. He is asking, some values are given. Ionization energy in kilojoule per mole. First ionization energy is 100 kilojoule per mole. Second is 200. Third is 1500. And is saying, what will be the formula of the chloride of the metal having the above values of ionization energy? Now what we have to do in these type of questions, solution will be, just write the ionization energy. We have ionization energy 1, ionization energy 2 and ionization energy 3, right. Now we know that this also, ionization energy 1 will be smaller than ionization energy 2 will be smaller than ionization energy 3. The values given to us are 100, 200 and 1500. Now you can see clearly the value is 100, next is increased by 100, but this one is increased by 1300. It means that we can eject the electron, the first electron, very easily by giving 100 joule per mole. Then second one is 200, that also we can eject, but 1500, the value is very high. It means that the valency of that metal is 2. That's why the formula of chloride that is, say the metal is M, so it is MCl2. So we will solve these type of problems in this manner. Let's solve another problem. Now in this question is saying that compare the first and second ionization energy of magnesium and aluminium. Now this is very important question. Generally in school exams you will find in your papers. So how to deal with the question? Let us start with the aluminium, writing their configuration, the aluminium and the magnesium. So magnesium, the configuration is, the atomic number is 12, the configuration is neon 3s2. And if we talk about aluminium, then aluminium atomic number 13, the configuration is neon 3s2 3p1. Now again that simple fact, magnesium is having completely filled S subshell and aluminium is having incomplete P subshell. That's why if we talk about the ionization energy 1 of magnesium, definitely it will be greater than ionization energy 1 of aluminium. Now we have to compare the ionization energy 2. And how we can compare? We have to eject out the electron. So we have to take Mg plus and Al plus. So we have to write the configuration. So magnesium plus, we have to write the configuration, and the configuration will be neon 3s1. So you can see it was 3s2. So for Mg plus it will be 3s1, right? For aluminium, aluminium was neon 3s2 3p1. For Al plus it will be neon. So from here the electron will be removed, we will get 3s2. So which is more stable, 3s1 or 3s2? 3s2 is more stable than 3s1, that is half filled. This is completely filled subshell. Therefore, if we talk about the ionization energy 2, the ionization energy 2 of magnesium, that will be smaller than the ionization energy 2 of aluminium. Now, what electron gain enthalpy is? It is the energy, either it is released or it is used when isolated gaseous atom accept an electron to form monovalent anion. Means, suppose we have a gaseous atom X. It accepts the electron and it forms X minus gaseous ion. Now, this is the enthalpy change. I have told earlier, enthalpy change and about the enthalpy we will discuss in thermodynamics, but for now, enthalpy means energy. If the sign is negative, means delta H is equal to minus Z kilojoule per mole. It means that it is releasing the energy. Means the process is exothermic. If the process is exothermic, the system is losing the energy and becoming stable, right? And if it is plus Z kilojoule per mole, it means that energy should be provided from outside to put this electron into the shells or the valence shell of this atom to make X minus gaseous ion. So it's pretty simple. If X is accepting the electron and forming X minus gaseous ion and energy is released, means it is becoming stable. It wants to accept the electron. But if we have to give the energy, it means that it was already stable and we are forcefully giving the energy, right? So, the large negative value of the electron gain enthalpy reflects that the greater tendency of an atom to accept the electron. Now, electron gain enthalpy is similar to electron affinity, but there is a difference of the sign. The actual relation is given in NCERT and the relation is delta H, that is electron gain enthalpy, negative of electron affinity minus 5 by 2 RT. T is the temperature in Kelvin, R is gas constant. But since you are in class 11th, you can use delta H is equal to minus of electron affinity, right? So, now its variation in group. If we go down the group, the size will increase and nucleus will not able to attract the incoming electron, because in between there will be so many electrons which will cover it, or it will cover the nucleus and they will not allow the electron to come inside. So that's how when we move down the group, the negative value of electron gain enthalpy will decrease. Now let's see the variation in period. Now let us assume the second period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So what is happening? We are increasing the atomic number. We are increasing the number of protons in the nucleus and size is also decreasing. So if number of protons are increasing and size is also decreasing, definitely the nucleus can attract that electron very easily. Therefore, the negative value of electron gain enthalpy will increase when we move across the period. So that was a trend in the group and the period. Let's see some important facts. First one, the values of electron gain enthalpy. Now, as we discussed, if we go down the group, the negative value decreases. But in the case of chlorine, sulfur and phosphorus, in the negative values of electron gain enthalpy of chlorine is more than fluorine, sulfur more than oxygen, phosphorus more than nitrogen. Why? Because the size of fluorine, oxygen and nitrogen, it is very small. If the size is very small, then when the electron will come, the already present electrons will repel that electron which is incoming to the valence shell. That's why, due to the compact size, due to the small size, it is very difficult for the electron which is coming inside to adjust in the valence shell. But on the other side, the size of chlorine, sulfur and phosphorus is big. That's why the electron gain enthalpy, I should say that the negative value of electron gain enthalpy of chlorine is more than fluorine, sulfur more than oxygen, phosphorus more than nitrogen because of their small size. And one more point, the electron gain enthalpy of oxygen is lower than all the elements in its group. This is a fact, and these things they ask in school exams and competitive exams. They will ask you exception only. Nobody will ask sodium is bigger than potassium or potassium is bigger than sodium. Nobody will ask these type of questions. They will ask you exception only. Now, another exception. Everybody know that nitrogen is non-metal, and non-metal has a tendency to gain the electron. But the electron gain enthalpy of nitrogen is positive. Do you know why? It is because half-filled p subshell. We know that half-filled subshells are stable, and if they are stable, then it is very difficult to put the electron in the valence shell of electron of nitrogen. Now, fourth point, electron gain enthalpy of alkali metals is negative, means the gaseous atoms of alkali metal will accept the electron, will tend to accept the electron. Why? Because their electronic configuration is ns1, and if they gain one electron, it will become ns2. For example, if you take sodium, sodium gaseous atom plus electron gives Na minus gaseous. If anybody asks you, is it correct? Yes, this is correct, because sodium is an alkali metal, it will gain the electron and it will be exothermic process, right? So, let us solve some questions. Now, which of the following has negative value of electron gain enthalpy? Means, which of them will try to accept the electron, easily accept the electron? So, helium is noble gas, it will not accept the electron obviously. Nitrogen, we have studied that it will not accept the electron. Now, if this question comes in exam, 90% of the student will tick option number 2 as the correct option, but that will be wrong. We have discussed in this lecture. So, nitrogen is not the correct option because it has half-filled p subshell, right? So, the solution, if we write, sodium is an alkali metal, calcium is alkaline earth metal. The electronic configuration of sodium, atomic number 11, that is 1s2, 2s2, 2p6 and 3s1. Now this 3s1 will try to become 3s2 because 3s2 is more stable than 3s1, and calcium is 20, and we can write in the condensed form argon 4s2. So this is already completely filled. Definitely it will not gain the electron. So this 3s1 will gain the electron to become 3s2. So our answer will be 3. So it is option number 3rd. Now what is electronegativity? Electronegativity is the tendency of an element to attract the shared pair of electron. Now what does it mean? We know that hydrogen has one valence electron and it needs one more electron to complete its duplet. And we know that chlorine has 7 valence electrons and it needs only one electron to complete its octet. So what they will do? Hydrogen is a non-metal, chlorine is also a non-metal, therefore they will share the electrons and they will form a covalent bond. But it has been noticed that chlorine attracts the electrons from hydrogen and this is called electronegativity. Now we have to know what is the reason behind it. The main factor on which the electronegativity depends is the effective nuclear charge and the atomic radius. Now we know that when we move across the period, effective nuclear charge increases and atomic radius decreases. Therefore, chlorine is more electronegative than hydrogen. That's why it has more tendency to attract the shared pair of electron towards itself. We will discuss more about it in the next chapter, that is chemical bonding and molecular structure. Now, the most common scale which is used to find out the electronegativity is Pauling scale. But how it all started? It all started with the Mulliken. Mulliken found the electronegativity and he said that the electronegativity we can find by taking the mean of electron affinity and ionization energy. So electronegativity is ionization energy plus electron affinity whole divided by 2. But the energy should be in electron volts. Now then came Pauling. The values of electronegativities, or the scale you can say, that was 2.8 times smaller than that of Mulliken scale. And on Pauling scale he said that electronegativity is ionization energy plus electron affinity whole divided by 5.6 and the energy is in electron volt. But the energy is in kilojoule per mole. In that case, it will be electronegativity is equal to ionization energy plus electron affinity divided by 540, right? So that's how we find the electronegativity of different elements. Pauling used one more formula to find out the difference between the electronegativities from where he got these all values of electronegativities of different elements. Which was the formula? The formula was XB minus XA means electronegativity of an element B minus electronegativity of an element A is equal to 0.1017 EAB minus half of EAA plus EBB and root of this whole thing. Now what is that EAB? EAB is the bond energy of AB. We are talking about diatomic covalent compound and that is AB. One element is A, another element is B, just like HCl, right? So the bond energy of AB is EAB. The bond energy of A2, that is AA, that is EAA, and EBB is the bond energy of B2. So if A2 reacts with B2 to forms AB, then we can find the relative, or you can say the difference between the electronegativities by this formula. So he applied the formula and he found electronegativities of the elements which are present in the modern periodic table, and some electronegativities values are there. Examiner will expect you to know, and the elements are these: hydrogen, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Now we all know electronegativities of fluorine is the maximum, that is 4. then chlorine it is 3, bromine it is 2.8 and iodine is 2.5. So you have to learn this. He will not give the value of the electronegativity. He will expect you to know, right? Oxygen it is 3.5, nitrogen 3, carbon 2.5, boron 2, beryllium 1.5, lithium it's 1, and more importantly hydrogen it is 2.1. So these are the values, the common values of electronegativities of different elements present in periodic table. There are some exceptions also. We know that in the period the electronegativity increases as the effective nuclear charge increases, and down the group the electronegativity decreases. So the exceptions will be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, this is second period, and boron, aluminum, gallium, indium, thallium, this is 13th group. Now in 13th group what happens? This is the electronegativities we just discussed. In 13th group, the electronegativities increases after aluminum. Like aluminum has the electronegativity 1.5, then gallium has 1.6, then it is 1.7 for indium, then thallium. In the carbon family, carbon has 2.5, silicon 1.8, germanium 1.8, tin 1.8, they are same, and lead 1.9. They will ask you question from here only, from the exceptions. Nobody will ask you which is more electronegative, fluorine or nitrogen. Nobody will ask you this type of questions. So they will ask you the question from exceptions, right? Now let's move on to next property, that is electropositivity. Now electropositivity is the property of the metal to lose the electron. Better is the electropositivity, better will be the metallic character, or better will be the electropositivity. For example, sodium. We all know that sodium loses electron and it forms sodium ion, right? So sodium is electropositive. Now we have to know what is the trend of electropositivity. In the period, as we move across the period, the effective nuclear charge increases. We are increasing the number of protons in the nucleus as well as the number of electrons in the shell. This thing we have discussed already in the atomic radius and ionization energy. So what will happen? Nucleus will tend to attract more the outermost electrons. So the metallic character will decrease. And as we go down the group, the number of shells will increase, and the number of shells will increase, electron, the valence electron will go far away from the nucleus, and the metallic character will automatically increase. So guys, let's solve one problem. Now in this problem he is saying, compare the electronegativity of the elements having the configuration 1, 2, 3, 4 options are given to you, and many times I have seen students comparing these electronic configurations and solving these type of problems. So my suggestion is, whenever you get this kind of problem, then you solve in this way. The solution now I will not see the electronic configuration. What I will do, I will make the element. The atomic number is 4. The total number of electron here is 5, right? It means that it is boron. This is boron, this is 11, this is sodium, this is fluorine, 2 plus 2 plus 5 is 9, 2 plus 2 plus 6 is 10, that is neon. Now we know that Fluorine is most electronegative. That's why this is the answer. So the answer is third. No need to look at the electronic configuration. Just write the element. And when you write the element, you will get the answer automatically. So guys, in this lecture, we have discussed about atomic radius, ionization energy, electron gain enthalpy, electronegativity, and electropositivity. Now, let's discuss about some more properties of elements. The first is the valence, and more oftenly we call it valency. Now, valency is the combining capacity of an element. Now, we have to see that how valency changes down the group and across the period. Now, first of all, let's see the variation down the group. Now, down the group, the outermost electronic configuration remains same. That means valency will also remains same. But across the period, it depends on two things. First is in which period it is present, and the second one with which element it is combining. For example, if we take the third period, means sodium, magnesium, aluminium, silicon, phosphorus, sulfur, and chlorine, they all are member of third period. If they combine with hydrogen, their valency will vary in this manner. First it will increase, then it will decrease. You can see by looking at their hydrides. Sodium forms NaH, magnesium forms MgH2, aluminium forms AlH3, silicon forms SiH4, then the valency decreases, phosphorus forms PS3, and sulfur forms H2S, and chlorine forms HCl. It means that first it will increase, then it will decrease. Now, if we talk about oxygen, with the same period, it will keep on increasing like 1, 2, 3, 4, 5, 6, 7, and the oxides will be Na2O, MgO, Al2O3, SiO2, P2O5, SO3, and Cl2O7. So it will keep on increasing. The reason behind it is oxygen forms double bond. Therefore, the valency of an element with respect to oxygen will be always more than that of hydrogen, right? Let's talk about types of oxides. Now, there are 4 types of oxide. The first is the basic oxide. Basic oxides are formed by the metals, and the example is Na2O. When we dissolve Na2O in water, it will form NaOH, and NaOH very strong base. Non-metal forms strongly acidic oxides. Now, for example, Cl2O7. We all know that if we dissolve Cl2O7 in water, it will form HClO4, and HClO4 is perchloric acid, and that is strongest acid in the world. Third type, amphoteric oxides. The metals which are not too much reactive, like aluminium, zinc, etc. They will form amphoteric oxide. Fourth one is the neutral oxide. There are only 4 examples like this: water, carbon monoxide, NO, and N2O. They all are neutral. Now, let's discuss about the anomalous behavior of the element which is present in the second period of a particular group. For example, group number 1, we have lithium, sodium, potassium, rubidium, and cesium. And if anybody asks you, do lithium form hydrated chloride, LiCl.2H2O? Yes, it will form hydrated chloride, but the other members will not. We will talk more about this in the chapter S block. This is just an information given to you, right? Let's move on to the reason behind between this. Small atomic size, first one. The second is the small charge to radius ratio. Third one is high electronegativity, and the fourth one is absence of vacant d orbitals. So all these things you will study in the chemical bonding, S block and P block. Right now what we are doing? We are just studying, we are taking small information about these type of properties of elements. Right? Now, next is diagonal relationship. The elements which are placed diagonally, they resemble each other. Their properties resemble each other. For example, lithium resembles magnesium in some respects. Lithium is the first group element, magnesium is the second group element. Lithium will resemble to its group member like sodium, potassium, rubidium, cesium, and magnesium will resemble to beryllium and calcium, strontium and barium, etc. Right? Now, if we talk about the elements which are diagonally placed like lithium and beryllium, beryllium and aluminium, boron and silicon, their properties, lithium magnesium, beryllium aluminium, boron silicon, their properties resembles each other, and the reason is their polarizing power is same. What is polarizing power? It is the ionic charge divided by the ionic radius. Let me tell you with an example. Suppose this is lithium ion. Now you can see that it is having the positive charge and there are electric fields having some gap between them. So this is the gap between the electric field and it is having some charge density. The correct word is charge density. So the charge density is determined the gap between the two lines of electric field. But if we talk about sodium, sodium is bigger than lithium. So the distance between the line will increase, means the charge density will decrease. But if we talk about the lithium and its charge density and magnesium 2+. So what we are doing here? We are increasing the size also, we are increasing the charge also. So overall, the charge density will remain same. The gap between the lines will remain same. That's why their properties are same. Lithium resembles magnesium, beryllium resembles aluminium, and so on. So this was diagonal relationship. So guys, this was the end of the chapter. We discussed about atomic radius, ionization energy, electronegativity, electron gain enthalpy, and electropositivity, their trends in the group and period. I hope you understood everything very well. The next chapter is chemical bonding and molecular structure. Till then, goodbye.